So here we're going to talk about fractional distillation. And in order to understand what fractional distillation is about, we need to understand with the starting raw material, and that's crude oil. So crude oil is what you start with, you dig it up from the ground, and it's finite, so it's going to run out. It's the remains of ancient biomass buried under mud, so plant life being crushed together to form crude oil over many, many years. It's a mixture. That means it's got lots and lots of different, mostly hydrocarbons involved. Remember, hydrocarbons are compounds which contain hydrogen and carbon only. And finally, most of those hydrocarbons, so most of what crude oil is made of, is a mixture of alkanes. So if I were to draw it simply, I may draw it like this. I may draw crude oil having some single alkanes, some longer chain alkanes, and some massively long alkanes. So crude oil is a mixture of all these different chains of alkanes. Now, if I was going to be a bit more specific about what these circles I'm drawing are, what they represent, well, this one here, I'm trying to say is a single carbon alkane. So it's methane, and it would look like this. If I'm trying to be specific about what this represents, well, this would be a 3-chain carbon, a 3-chain alkane called propane. And so as you can see, crude oil can contain some really, really long alkanes, some massively long chains of carbons, but it's all a mixture. So that's what crude oil is. Now here's the thing, this mixture isn't particularly useful because it's got so many different compounds, and these compounds, for example, this compound with 1 carbon is different to this compound with 3 carbons, which is very, very, very different to this carbon with, say, 10 carbons, and this hydrocarbon with 10 carbons. So these different parts of crude oil, these different compounds in the mixture, have very different properties. So we need to do something, we need to do fractional distillation that separates out these compounds because they all have different properties. Okay, so here we've got what we call our fractionating column, and this is going to be able to separate out the different compounds in crude oil based on the size and their chain, because that then has another property. So what we're going to do, we're going to insert crude oil into the bottom here, okay? And what we're going to do is we're going to apply heat. Now it's important you don't say burn here, because burning is a different thing to heating. Heating something up is you're going to evaporate the liquid and turn it to a gas. Okay? Burning something is a reaction with oxygen combustion, and you create different products. So what we're going to do here is, with our mixture of different hydrocarbons or different chains, we're heating them up so that they evaporate. So here is we're going to evaporate the different parts in crude oil. Now what we actually find is that the shorter the chain, the lower the boiling temperature. So these short chains like methane with 1 carbon will boil at a lower temperature than these really long chains. Now, by applying heat at the bottom, it will make the bottom of the fractionating column really hot, whereas the top of the fractionating column will be substantially colder, and you'll set up a temperature gradient here. So what happens is, when the crude oil evaporates, and you get different vapours evaporating off, they condense. That means they turn back from a gas to a liquid, okay, at a certain temperature. So a medium length carbon chain will condense around the middle of the fractionating column, and where it's a medium temperature. A really small length carbon chain where only you've got 1 or 2 carbons, will condense right at the top, and the really, really long chains will condense either right at the bottom or won't even evaporate properly at all, so it will come off at the bottom. So therefore you're going to be separating out the different chains based on their boiling point, and when they condense, the temperature at which they condense. Now each different carbon length chain coming off at each point is called a fraction. Okay, hence the word fractional distillation. And so the top fraction, your smallest chains, are things like refinery gases and liquefied petroleum gases. And these are really small chains, such as methane, propane, butane, and they can be used in cooking gases. Now, the next one that might come off is a fraction called petrol. You may have heard of it. And this chain has about 6 carbons in length, so it's a bit longer, and yet it's really useful for fueling cars. Now, other fractions that come off are ones called kerosene, diesel, fuel oil. And so as you go down here, these carbon chains increase in length. So as you approach the bottom and you get to fractions like bitumen, these are incredibly long carbon chains, and therefore they have an incredibly high boiling point, and so they're not likely to condense in this fractionating column. So just to add a few more comparisons between the different fractions, we've already said at the top of the fractionating column they're small chains, at the bottom they're long chains. We've already said the top have a really low boiling point, and at the bottom they've got a high boiling point, and this is what enables you to separate them out. The ones at the top are really flammable. So for example, methane, ethane, propane are really flammable gases, whereas bitumen is quite hard to ignite, so this is less flammable. And finally, we talk about the word viscous in terms of runniness. So if something's really runny, it's not very viscous. So the fractions at the top are runny, whereas bitumen is quite gloopy, it doesn't run very much. So we can say bitumen is viscous. So in summary, that's how it works. Fractional, because we're splitting crude oil into its fractions, into its parts, because crude oil is a mixture. And distillation, because the processes that going on are we evaporate and then we condense. Okay, so we've got evaporation and we've got condensation. So we turn liquids to gases and gases back to liquids, which is why the boiling point is so important. Thank you.